السلام عليكم أعضاء السادة الحضور، أعضاء منتدى الثلاثاء الثقافي، ضيوفنا الكرام. أهلا وسهلا بكم في أمسية جديدة ومتجددة من لقاءاتنا الأسبوعية لهذا اليوم الثلاثاء المصادف مارس 31 2026. ضيفنا اليوم الدكتور إحسان الطائي، ضيف عزيز من كالجاري، يشرفنا اليوم بمحاضرته الأولى معنا في هذا المنتدى. قبل ما يبدأ الدكتور إحسان، أحب أعطي نبذة مختصرة عن سيرته العلمية الحافلة بالنشاطات والبحوث. الدكتور إحسان الطائي من خريجي جامعة الموصل، اختصاص الكيمياء، ولديه شهادة دكتوراه من جامعة مانشستر في يوكي عام 1992 في الماتيريال ساينس كورشن انجينيرنج، ولديه خبرة كبيرة أكثر من 35 سنة في البحوث والتكنولوجي والتطوير والانوفيشن مانجمنت. لديه العديد من البحوث والمنشورة والنشاطات العلمية المتفرقة في مختلف المجلات العلمية المعتبرة. عمل في العديد من المؤسسات والعديد من الجامعات. عمل في Canadian Ministry of Natural Resources بين عام 1992 وعام 2001، وعمل في شركة أرامكو السعودية ما بين عام 2001 و 2021 as Chief Technologist، وعمل في جرين إنوفا بالبحرين منذ عام 2021 لحد الآن، وكذلك في مت اي سي جي كندا من 2023 ولحد الآن. وساهم في تأسيس أو تأسس 3 Innovation Centers في كامبريدج يوكي، وكينج عبد الله يونيفرسيتي بالسعودية، وجامعة بوسطن بالولايات المتحدة الأمريكية. الدكتور إحسان لديه العديد من النشاطات الحافلة العلمية، واللي راح يشاركها اليوم معنا في موضوع الأدفانس ماتيريال. نتمنى لكم مشاهدة ممتعة ومحاضرة طيبة مع الدكتور إحسان. تفضل دكتور إحسان.
شكرا جزيلا أستاذ عمار، بارك الله فيك. تحياتي للجميع وبارك الله بكم. طبعا it gives me a great pleasure to be with you مع هذا التجمع الطيب إن شاء الله، ونساهم معكم بجزء من مرحلتنا العلمية والعملية. اختاريت اليوم presentation about advanced material. طبعا when I do the presentation I'm going to turn off the camera، وما راح أشوف يعني التفاعل. إذا أكو سؤال أو استفسار فأرجو من الأستاذ عمار يوقفني بالصوت إذا أكو فد شيء تعليق أو أي شيء من هذا القبيل. بسم
احنا
الله الرحمن
عادة
الرحيم.
بعد المحاضرة نعطي مجال للأسئلة، فخذ راحتك.
نعم، لا إذا أكو شيء توضيحي يعني استفسار توضيحي حتى لا تنسي، إذا أحد عنده
اوكي.
يحب إنه أنا أوضح شيء يوقفني أستاذ عمار.
تمام.
شكرا. أنا now I will switch on my computer the other side. Okay, as you can see on the screen, this is basically I'm going to talk about the advanced material towards next generation of materials. So the purpose of this presentation is basically to look forward on what is next. Yani, nowadays we know and we have dealt in the past with different materials, but as the technology advanced very quickly during the past decade or so, the materials also there is an area of advancement in it. and we may be hit in the future in a new generation of materials. So what we look at, or what we're going to cover today in the presentation, is basically we're going to go through materials evolution, which is the timeline of material, looking at advanced design of material. What are the industry pull? We will explore together the industry pull and the industry drives in the material innovation. And then we will look at the smart functionality, and then we will end up with the market impact at the end. So before we start diving into the agenda, when we talk about advanced material is a very relative term. And what is advanced materials 100 years ago is not anymore advanced material today. And what is advanced material last decade, it may not be valid today. So because it's a relative term, so we will go through the timeline. We have to go through the history and understand the materials throughout the history. And with this, what we will look at, we have to ask our question first: how advanced is the advanced material today? So that question we will be answered at the end of the presentation, or towards the end of the presentation. Is really advanced material are advanced today or not? And the second question that we need to answer: who creates who drives the innovation in this industry? Is it innovation creates the industry needs, or the industry needs drive the innovation? So which one is the academia create new materials or do research, and then the industry use it and advance in the material, or the needs of the industry actually drive the research in the university towards discovery of a new material? So we will this question too, we will answer it towards the end of the presentation. So let's keep those two questions in our mind and how we're going to address them later on. So in order to answer this question, let's go through the materials timeline and history. We start with a prehistoric until the Stone Age, which is about 3,300 BC. So this could be, because it's prehistoric, there is no record in the history at that time. So we don't know when it started, the materials, but it's a prehistoric. It could be 2.5 million years ago, or it could be a few thousand years. We don't know. It's a prehistoric until 3,300 BC, which is amount of thousand, if it's not millions of years. So it was a Stone Age. So really, the importance of material, because it's impact our life, they name ages based on materials, or based on the dominant material and its impact to that age. So the Stone Age, from the name, they used the main dominant material for daily life. It was a stone, whether to prepare a weapon or to do whatever, they use the stone as the dominant material. From 3,300 BC to 1200 BC, there was the Bronze Age, which is about 2,100 years duration. Basically, it's a copper plus tin that produce you alloy of bronze. But this is not the only material that was used during that era or that age. There were ceramic, gold, papyrus, and silk, all other types of material available there. But the dominant at that time was bronze. So that's why they call the Bronze Age. Then it follows by Iron Age, 1200 BC to 300 AD. The main dominant material was iron, and also there were available the glass, processed minerals. And this age is duration is about 1500 years. This was followed by Middle Ages with a 300 to 1300, basically 1,000-year-old or duration of porcelain age in the Far East. The porcelain plus there were metal and ceramic composite at that time. That was the dominant 1,000 years. There was no new discovery during that age that impact the society in terms of metal other than iron at that time. Then becomes the steel, or what we call industrial era, which is 1300 to 1950. The steel age, which is basically the foundation of the major industrial revolution. The alloying of iron, adding different metals to it, different alloying elements, making different types and different grade of steel, really boost everything in the industry, from building to automotive to trains, railway, name it, ships. It's all impacted by this, the industrial revolution, the steel, and also building, manufacture, smelting, that led us to discovery of other alloys and other materials. The impact is huge, and the duration of this age is 650 years. Then in 1950, the discovery of silicon led to an info age, which is the silicon age or the semiconductor age. I put a question mark because either still going or we are in a transition to other materials. This impact actually accelerate industry tremendously, because the electronics that facilitated everything in our life, from communication, automotive, appliances in our house, everything communication is impacted by the silicon and semiconductors. But it's not the only materials, though, as reflected in every different era or age. There were modern composite, polymers, nanostructure, material, and meta materials. So we basically went from this stone to bronze to iron and steel, and we've gone into today's material, which is composite and other advanced material. However, what we learn from the timeline, if you can look at the duration of each age, as we move from one age to another, there is a significant drop in the duration. So we went from probably million year to 2,100 year duration of age, 1,500, 1,600, and now we are about 76 years in the info age or the silicon age. Therefore, I mentioned also in that material, I mentioned metamaterials. I don't know, I don't see you all, but metamaterial, I don't know if most of you know what is metamaterial, but let me explain what metamaterial is. Metamaterial, this is an overwhelming text slide, but I don't want you to overwhelm. So I highlighted, focus only on the highlighted text. So the blue text is the most important text. Metamaterials is basically an engineered material that is engineered to have properties that is not found in natural occurring material. They are made from assemblies of multiple element, which is composites, either composite material, whatever, two different types of material, you mix them together or more, you got a composite. And the basic one that we use everywhere is the metals and plastic, but there is plastic and ceramic, there is carbon fiber and other composite material. And thirdly, we have I'm sorry, there is an interference. Okay. They are precise shape, geometry, size, orientation, and arrangement of this material give them their smart property and capable of manipulating. This is very important here. We have to focus. Give this material the capability of manipulating electromagnetic waves. So either by blocking, absorbing, enhancing, or bending waves to achieve benefit that goes beyond what is possible with conventional material. So they engineered this metamaterial to give it a property that is basically they change the shape, geometry, size, orientation, and arrangement of this material. So it can block, absorb, enhance, bend the waves of electromagnetic waves. This material should pave the way for conceptually new range of radio, microwave, and optical technologies with a broad application. Metamaterial exhibit multiple function, multifunctional characterization that can, or characteristic that can be engineered to satisfy prescribed requirement. Their new properties are activated by specific interaction with electromagnetic field or because of external electrical stimulation. So either when it's exposed to electromagnetic field, it responds to what is designed for, or it has an external stimulation by electrical current. Research in this area entails opening a new multidisciplinary field of a study embracing material physics, electromagnetic optics, radio engineering, and electronics. So all these fields now are open to advance based on metamaterials. So this is why I mentioned it in the info technology box or info age. I mentioned the metamaterial because the impact is basically on the info age or the info related age. So either we are continuing in this age or we're going to transition to a new age soon. So let's look again about the needs of industry today. So if we ask ourselves, what is the need of the industry to material? So in order to answer this question, we have to go and inspect every sector. So if we go to health sector, what is the need of the industry in health sector and environment? Basically, they are looking for circular carbon economy. Their needs is based on controlled degradability. Let me explain what is controlled degradability. Because of the environment, there is the concern about plastics. Plastic is impacting negatively the environment. So there is a notion of why don't we make the polymer degrade, but in a controllable way, such as if it hits a saline environment like seawater, it can go back to its origin, which is methane gas and whatever other materials. So it degrades itself when it hits certain environment or say certain pH or even certain temperature, or if it's electricity, whatever it is. So this is what I meant by controlled degradability. Heavy metal removal and clean water. This is a need for heavy metal removal from the industry. Disease control, also an area where the industry are in need for a new material to control disease. In the energy sector, definitely there is a huge need for renewables, harvesting energy. Energy is not only solar, we can get energy and harvest energy from different temperature zone, from vibration, from pressure, from all kind of different differentiation, then we can get or harvest the energy by creating material that can harvest this energy and store it. Also, we need a storage material, a material that can store a large capacity of charge and very fast. Efficiency. Energy sector is dying for efficiency is the lowest efficiency industry or sector in the currently. Intelligent asset integrity monitoring system. The monitoring system, because energy, it's the nature of this sector is spread all over vast land. So in order to respect all this, like even high power cable, it goes from continent to continent. So how do you inspect that? How to clean it? How to repair it? All this, it requires an intelligent asset integrity monitoring system that can cover all the spread of this energy infrastructure. Now we move into transport. Transport also, they have need for autonomous vehicle, high speed transportation, but yet safe. So this is a challenge for that industry. Building and construction, material that can resist earthquake, material that can be energy efficiency or provide energy efficiency within the building, a durable material. Let me pause here and share with you a funny story. I don't know if it's funny, but durability. If you look around through age history, are we really producing a more durable material than in the past? The question that we should ask ourselves. If you look at the ancient civilization in Egypt or in Iraq, there are building and there are materials there that is still standing in a perfect condition from thousands of years. And there is a slab of concrete that is in Babel. It was pictured by one of the explorers there and posted about 30 years ago in the internet. And it caused big controversial because that slab, it was built the Babel civilization was 4,000 BC, so about 6,000 years. A slab of concrete. طبعا الكونكريت, that slab of concrete in Babel, it wasn't like cement. It was aggregate plus some fibers, maybe hay and clay. But if you examine that over 6,000 years, there was no single crack in that slab of concrete. However, you go and look at the bridges in North America today, after 25 years, all full of patches and cracks, and they have to repair it. So what is the secret between ancient history and today? It was found in في مسلة حمورابي. Hammurabi, they discovered that there is a law written at that time specifically for building. And one of the laws that is said there by Hammurabi, if a builder build a house to a citizen and the house was occupied and then the house collapsed, then the builder have to build another house free of charge to the citizen. However, if the house collapsed and killed the owner, then the builder will be killed. If the house collapsed and killed the wife of the owner, then the owner will take the wife of the builder. So that's the funny story, which is basically led to an impeccable material development and building and construction. So this is just a diversion of the presentation. And then in the building and construction, we have to consider other pole, which is the high-tech ready. What do we mean by high-tech ready? We saw the advancement in technology today. You go to a building today and then you lose the Wi-Fi signal if you are a little bit away from the modem or whatever the signal. It's lost. The building, it's not friendly to the advanced technology of today. So all the building have to reconsider the building material to be high-tech ready. That is a concern from the building and construction industry and from the high-tech industry, both of them. They identify this as a challenge and a needs for the development of material. In the electronics, of course, there is a need for flexibility, flexible electronic material, responsive that can, these materials should be responsive to different environments, and they need for high speed. Somebody may argue, what high speed higher than what we have as fiber optics? Well, not only high speed in terms of transmitting data, but in terms of calculating data. So we need material that withstand high temperature for quantum computing, highly conductive material in the quantum. The reason why quantum computers today is very, very, very expensive is not because of its complicated technology. It's because of the cooling system that it requires to cool it down, because the temperature goes extremely high when you start the quantum computers to do the calculation. So after we're looking at this is just example of some sector. There are other sector like the pharmaceutical. They need much quicker drug discovery. They need a lot of other things. This can be expanded, but I selected only 5 for the purpose of giving it as example where the industry actually has a real need today to develop material to cover all these needs. Now we move on to advanced material now. And we try to answer these questions that we put in the beginning. How advanced is the advanced material today? What do you think? I think certainly there is a need for more advanced material than what we have today. There is a big room for opportunity to develop and discover more advanced materials in order to meet the need of the industry. It's not any more advanced, the advanced material that we have today in all sectors. The second question that we asked in the beginning, does innovation create the industry need or the industry need drives innovation? In my opinion, maybe someone will argue, I would say both. They are the driver. I give you an example. The nanotechnology, when it's discovered, is not a pull from the industry. It was discovered and worked on in research by professors in university. Basically, the buckyball, it was in Rice University in the United States. That was the trigger of the nanotechnology at that time. And then when the property was demonstrated after studied and researched at universities, the industry start to focus and put attention to that material and find application for it, how it can serve the industry. And on the other hand, so that's an example of how academia drive the need for the industry. And on the other way around is when the industry have a serious need, most of the professors in the university will ask for a grant from the industry in order to do in-depth research in that area and create new materials. and that is the other drive. So in my opinion of both, you may argue about this, but that's, I give you two examples. Now, let's look at the future materials, which is the next generation of material. How do we expect them to be? Now, if you recall the slide, the needs of every sector in the industry that we went through, what are the needs of this industry? Then we will have a pretty much good feel of what the characteristic of the new material or next generation of material will be. So, for example, the characteristic of a future material should have some sensing capability. So the material is not, it should be active. It should have embedded sensor in it to sense the surrounding in order to provide response. So it have to have a responsive kind of material. So we embedded sensor. It has to have a responsiveness to the environment or to signal. Active and adaptive. So the material cannot be shaped once and that's it. It stays there inactive. No, it have to be active and adaptive also. Flexible yet strong and self-healing. Those are the main characteristic of how we envision the new material or next generation material. So what are the examples of adopting such materials today that can address these characteristics? It's basically carbon nanotube that we have today is already available and already manufactured. 2D materials, which is similar to graphene oxide, and they are a derivative. Those material actually they provide the flexibility and the adaptability and the functionality and the responsiveness. Those 2D material is amazing material. Polymers, it gives the flexibility and it gives the mechanical and environmental kind of responsiveness. We can control them much better than rigid metal. Carbon fibers and composite, also another material that can be utilized. MOFs, which is metal organic frameworks. This material can be a great material for carbon capture or catalyst or many other application. So with this available material and this characteristic, what can we do? Is the new generation material is going to be one kind of material? The answer is no. It's not one material. It has to be multiple material in sync with multifunction structure plus plugged into AI. AI that will provide the responsiveness, the change in shape, the functionality, the adaptability, all these kind of things will be controlled by AI. This is not kind of science fiction. No, I'll show you later on. This is going to happen. I'm confident it's going to happen, or it's going to be created. We always learn from our bodies or from nature, different nature. So, for example, a human being has a wonderful nerve structure that provide this body five sensing transmitted through our body, which is totally different media. For example, we sense audio signal by hearing. This hearing is transmitted to the brain by a nerve through a nerve system. Same nerve system transfer photon, which is our eyes, the vision. Same, it's not fiber optics. it's a nerve system. It takes it to the brain. Chemical detection by our noses. We detect smells and different chemicals, and it transmitted by the same nerve system. Test of buds in our tongues. We test food. We test different things, sour, sweet, whatever it is. And it transmitted same nerve system to the brain. And then we test the pressure and temperature and all kind of the environment and even wind and whatever it is by our skin, which is covered by millions of nerve endings. And we can detect the smallest thing by these nerves, smallest change in surface roughness, smallest temperature change. All this is transmitted through the nerve system. So, and the nerve system is not copper cable, is not fiber optics. It's basically organic material. Nerve system is mainly cholesterol. The main constituent of the nerve is cholesterol plus the connection with some minerals, and it uses some calcium and whatever it is, potassium, to connect or transmit the signal. It goes into our brain, interpret that signal as an audio, we hear sound, or as a vision, we see things, or as a test of chemicals or temperature change, all, and it responds very quickly in a fraction of seconds. So this system, if we learn from it, we can form material, plug it into AI, and we will have a similar way. I'm not saying we're creating another human being. No, I'm just saying we can control material by having it in some way or another, have some signal transmission through it, and itself has some functionality in order to be smart material. So smart material, they are responsive, adaptive technologies. Basically, their dynamic response is react to temperature, light, pressure, or chemical changes, shift shapes, colors, or stiffness in real time. And high impact application enable morphing aerospace structure, self-adjusting biomedical implants, and interactive consumer products like color changing fabrics. So imagine you have a tie and the same tie, whenever you wear a new jacket or a new shirt, it will change to match that color or to have it compatible color to that without changing the tie itself. So that is kind of materials, when we say it's a smart material. Industry 4 readiness, pairing sensors with responsive element, accelerate adaptive system, and smart infrastructure. So all this until now, it sounds like science fiction. Oh, it cannot be done. But let me share with you a real picture of a research that was done at the Institute of Composite in Germany, Institute of Composite Materials in Germany. This is an actual scanning electron microscope pictures. The scale is right here, is 500 nanometer, that length of line. And this composite material, it consists of carbon fiber or carbon nanotube. This is for electrical conductivity, graphite for solid lubricant, polymer matrix for component joining and for thermal resistance, short carbon fiber for stiffness and strength. So this is one type of composite material that is actually researched about 10 years ago or more in Germany. And they are advanced now. They are much, much advanced than any other institute. So they are towards producing a real smart material. So a smart material is not the only material. There is the quantum material that's on the horizon also is being researched. And it has a great potential. The quantum materials basically, a quantum material exhibit properties governed by quantum mechanics such as superconductivity, topological state, and entanglement, opening pathways toward revolutionary technology in computing, sensing, and energy. Research is uncovering material like topological insulator and 2D material with robust quantum features. These material promise breakthrough in a quantum computing hardware and ultra-efficient energy system. In-depth exploration of quantum material is basically a potential application require detailed textual explanation due to complexity and emerging research. So in basically what it is, to simplify it, quantum material is, it has a composition, a certain composition, and it has certain defect and disorder continuously, but it's not static, it's dynamic defect and dynamic disorder. And it has structure and symmetry that also can change according to the defect and according to the signal, which is it receiving a program in order to achieve certain property. And the oxidation state, which is when it interact with the entanglement of material, it produce this quantum material that is really the base material that will be relied on for quantum computing to become more viable in the industry. So with this, I would like to summarize very quickly. I hope I did not exceed the time. In summary, many sectors are phasing out the dumb and structural material. Composite have a great opportunity due to their beneficial property and status in high performance industry. There are numerous different functions being explored at different stages of technology readiness today. The global market drives, sorry, Abdullah, I will answer you. Just let me finish the last word. A global market drives the connectivity, electrification, automation, lightweighting, high-speed computing, and all they are all excellent kind of pull factors to drive towards a new next generation of material and advanced material. Okay, with this, I thank you very much, and hopefully I will be able to answer some of the questions.
شكرا جزيلا دكتور إحسان على هذه